Hello everyone, my name is Joost Romijn and I'm a PhD candidate at the Delft University of Technology, which is located in the Netherlands. Our work is titled Resistive and CTAT temperature sensors in a Silicon Carbide CMOS technology. The first question, of course, is why use silicon carbide? Silicon carbide is a wide bandgap material of which there are several. In the scheme on the top right of this slide, a selection of wide bandgap materials is given. Silicon carbide and gallium nitride are currently the two most researched options. The graph on the bottom left compares silicon carbide and gallium nitride and pinpoints specific applications. We see that these applications move closer and closer towards the edge of what is possible in silicon. This typically involves harsher environments such as high temperature operation. We therefore use silicon carbide to target today's challenges. It is also the most mature technology of the two options, and since industry is already adopting it in some discrete components, it also is becoming more cost effective. In research, we've seen that silicon carbide has been used for temperature sensors, optical sensors, pressure sensors, and more. However, if you would actually apply these sensors in a harsh environment, you would have your sensor in a harsh environment, your readout electronics silicon in the not harsh environment, and a relatively long cable in between. A more optimal solution, of course, would be to have your readout electronics on the same chip as your sensor. But this requires silicon carbide integrated circuits, which is something that is currently lacking. Fortunately, Fraunhofer ISB in Germany has developed a 6 micrometer CMOS technology that is being run in 4H silicon carbide substrates on 6-inch wafers. The multi-project wafer on screen is a 4-inch wafer from a previous run and is also where this work is part of. Regarding the temperature sensors, we investigated doped layers in the CMOS design layers that are implemented by ion implantation. We first compare in figure A a polysilicon layer with a highly doped N region, or the shallow N layer of the CMOS, and we saw a comparable difference in resistance change. However, the highly doped N layer has a negative TCR and is non-linear within this range. We then also compared the highly doped P layer, or shallow P layer, which has a much larger change, but again a negative TCR and also is non-linear within this range. We then implemented a CTAT sensor by using CMOS devices in figure C, and we have there a more linear response over this temperature range. We then also investigated a single inverter at room temperature and at 200 degrees, and we see a negligible change in its performance, which is very promising if you want to implement readout electronics on the same chip of the sensor. With this, I would like to thank you for your attention, and if you have more questions, you're more than welcome to come visit our poster presentation.